Assalamualaikum warahmatullahi wabarakatuh. My name is Madina Safabita HAMZAH. We are from Group 2, are going to present about electron beam lithography method in military application. Starting with the introduction of the application. Military technologies requires precise fabrication of nanoscale components for various applications such as sensors, communication system, and advanced materials. Nanoscale component is very crucial to improve detection and secure communication in military. Electron beam lithography (EBL) offers high-resolution patterning capabilities suitable for manufacturing intricate nanostructure used in military device. EBL is great for creating very detailed patterns needed for making small parts in military equipment. So the picture below shows the nanotechnology in military. Moving to the nanoplasmonic sensor device, it detects and analyzes chemical, biological, or physical phenomena. It also deals with the manipulation of light at the nanoscale using metal nanostructure, typically made of gold or silver, and it can be integrated into soldier uniforms, vehicles, and equipment for real-time monitoring of battlefield conditions. So, this is actually nanoplasmonic phase, which are materials structured at the atomic scale to interact uniquely with light. So this material change color when exposed to certain chemicals.
Next, we move to examples of nanoplasmonic sensor in military applications. The first one is chemical and biological warfare detection. Nanoplasmonic sensor can detect trace amount of chemical and biological agents such as bacteria, viruses, or toxins with high sensitivity and specificity, enabling rapid threat identification in battlefield environments. The second one is it also can use for explosive detection. Nanoplasmonic sensor can detect explosive materials, including improvised explosive devices (IEDs), by identifying specific chemical signatures. Can be integrated into portable devices or unmanned vehicles for real-time field monitoring. Next, personal protective equipment, which can be integrated into wearable devices or PPE to provide real-time alerts for chemical or biological threats. Lastly, for remote sensing and surveillance. This sensor in unmanned aerial vehicles (UAVs) or satellites can monitor environmental changes, providing valuable military intelligence.
Next is the introduction to electron beam lithography (EBL). So EBL is a technique for transferring a pattern onto a substrate surface. It involves scanning a thin layer of resist materials on the substrate using a tightly focused and precisely controlled electron beam, followed by selectively removing the exposed or non-exposed regions of the resist in a solvent. EBL enables the creation of very small features, often with dimension ranging from sub-micrometer down to a few nanometers. It can cover selected areas of the surface with resist or expose otherwise resist cover area. So this figure shows nanometer features created by EBL.
Diagram of electron beam lithography EBL for overall. First, including FIB implantation, KOH wet etching, hybrid structures, 3D structures, and suspended structures. FIB implantation. First and foremost, ion source. FIB utilizes a focused ion beam generated typically from a gallium Ga+ ion source. The ions are accelerated and focused into a fine beam. Second, substrate preparation. Similar to EBL, the substrate, often semiconductor material like silicon, is prepared with a suitable resist or mask layer. Third, implantation process. The focused ion beam is scanned over the substrate surface. The higher energy ions penetrate into the substrate material, altering its physical and chemical properties. This process is used for precise doping of semiconductor materials to modify their conductivity or other characteristics. Fourth, advantages. FBI implantation offers high precision in ion placement and lift control, allowing for complex doping patterns with minimal damage to surrounding areas. KOH wet etching. First and foremost, etchant solution. Potassium hydroxide KOH is a common etchant used in wet etching processes. It selectively etches silicon Si along specific crystallographic planes, particularly the 100 orientation. Second, substrate preparation. The substrate, usually silicon, is cleaned and prepared with a suitable masking material such as silicon dioxide or silicon nitride to define the areas to be etched. Third, etching process. The substrate is immersed in a solution of KOH at an elevated temperature, which means typically around 80 to 90 degrees Celsius. KOH preferentially etches silicon along its 100 crystal planes, resulting in anisotropic etching. Fourth, control and applications. The etching rate and etch profile can be controlled by varying the KOH concentration, temperature, and etching time. It is a critical process in semiconductor fabrication for creating features, channels, and precise geometries in silicon substrates. Hybrid structures. Hybrid structures combine materials like semiconductor, like silicons, metals, gold, oxides, polymers, and biological materials to leverage unique properties such as conductivity, transparency, strength, or reactivity. Different materials are strategically integrated to enhance device performance in electronics, photonics, sensors, biomedical devices, and energy system. 3D structures involves stacking or patterning materials in multiple layers or levels, creating complex geometries beyond traditional planar structures. Techniques include additive manufacturing, 3D printing, layer-by-layer depositions like atomic layer depositions, and etching processes, example deep reactive ion etching to build structures vertically. Suspended structures are created using techniques such as sacrificial layer etching. This involves depositing a sacrificial materials, often a polymer or oxide, onto a substrate and then patterning it to define the desired structure. The substrate, usually silicon, is cleaned and prepared with a suitable masking material such as silicon dioxide or silicon nitride to define the areas to be etched.
There are six working principles for the electron beam lithography. Firstly, electron beam generation. An electron sources will be generated into a stream of electron. Secondly is beam focusing. The electron beam is accelerated and tightly focused using electromagnetic lenses and apertures. And thirdly is resist coating. The substrate is coated with a thin layer of electron-sensitive resist to enable a high-resolution patterning, selective processing, and precise control over the exposure and the development stages. Next is pattern drawing. The electron beam is scanned across the resist using a scanning mirror to precisely draw the desired pattern. And after that is resist development. The substrate is immersed into a developer solution which selectively remove either the exposed or unexposed resist. There are two types of developer solution, and it depends on the type of electron beam. For positive electron beam resist, the exposed area become more soluble in developer solution. And a common developer for positive resist is tetramethyl ammonium hydroxide, and also methyl isobutyl ketones and isopropyl alcohol mixture. This mixture is often used for developing a certain positive resist like PMMA, which is polymethyl methacrylate. Next, for negative beam resist, the exposed area became less soluble and the unexposed area are dissolved by the developer. Common developer that is used for negative resist are methyl ethylketen and ethanol mixture, and also xylene, which is sometimes used as a developer for negative resist, especially if it has a thicker layers. Finally is pattern transfer. The pattern resist will act as a mask for further process like etching or material deposition, and it will transfer the pattern onto the substrate. This picture is an example for the working principle of electron beam lithography.
Next, characterization of EBL body samples involves scaling electron microscopy (SEM), which displays surface morphology and topography of miniaturized structure with high resolution, revealing details like feature size, shape, sidewall profiles, and surface roughness. Next, transmission electron microscopy (TEM) is a useful technique for analyzing nanomaterials, size, morphology, crystallinity, and composition, including metal dielectric interfaces in plasmonic sensors.
Let's know about specific characteristics about electron beam lithography. First, high resolution. Electron beam lithography can achieve nanometer scale resolution and allowing for the precise patterning of features at the micro and nanoscale. Next is multi-layer patterning that capable of performing multi-layer patterning with high alignment accuracy, and last is geometrical capability that can pattern a wide range of material including metals, semiconductors, insulators, and polymers. So that's all from us. Thank you for listening.